All right, here we go with another question. This is question number 4 from the 2016 AB International Exam. As you can see, this is not no calculators allowed on this one. So let's jump into it. Consider the differential equation dy dx equals y minus 2 times x squared plus 1. Okay, we've got a differential equation. Find y equals g of x, the particular solution to the given differential equation with the initial condition that g of 0 is equal to 5. Now I know for my calculus students and I, we've just finished this unit, and so I would hope that everybody would recognize this as a differential equation. And because the x's and y's are combined on the same side, this is not a simple differential equation. It's probably separable. So we're going to try separating the variables. We're going to multiply both sides by the dx. So we've got y minus 2 times x squared plus 1 times dx. With separable differential equations, you need to get all the y terms on one side. So dy over y minus 2 equals x squared plus 1 times dx. We have successfully separated the variables. Everything with a y or a dy is on the left-hand side. Everything with an x or a dx is on the right-hand side. Your next move is to integrate both sides. Now, one of these sides is going to be easier to work with than the other. You're probably looking at this and saying, oh, that's the side I know to work with. Good. Well, I'm also going to take a moment to rewrite the left-hand side as 1 over y minus 2 dy. The integral on the left is x squared plus 1 dx. Haven't done anything other than just rewritten this. Now we integrate both sides. The integral of 1 over y minus 2 is the natural log of the absolute value of y minus 2. The integral of x squared plus 1 is 1/3 x cubed plus 1x plus your constant of integration. You could solve for y right now and then use the initial condition, or you could use the initial condition and then solve for y. Doesn't matter to me. The initial condition says that g of 0 is equal to 5. So that means that if x is 0, y is equal to 5. So we have the natural log of the absolute value of 5 minus 2 equals 1/3 of 0 cubed plus 0 plus c. The natural log of 3 is equal to c. Okay, so now we have the natural log of the absolute value of y minus 2 is equal to 1/3 x cubed plus x plus the natural log of 3. That's great. Remember, what we're trying to do is we're trying to solve this problem. We're trying to solve for y. So to get rid of the ln, we're going to exponentiate both sides. E and the ln, these are inverse operations. They do cancel. And you get the absolute value of y minus 2. Now you've got e to the 1/3 x cubed plus x plus the natural log of 3. And you might be tempted, and you should be tempted, to think, gosh, there's something I can do here with the e and the ln. There is. Although we were able to cancel out over here, it doesn't work that way over here because you've got e raised to the power of all this stuff. If, however, you rewrite this as e to the 1/3 x cubed plus x times e to the natural log of 3, now that is legal because we're writing this now as e to a power times e to a power. When the bases are the same, the rule is that you add the exponents, and so you'd get back here. And now we've got that cancellation that you see. E raised to the power of the natural log of 3 is just going to be 3. So the absolute value of y minus 2 equals 3 e to the 1/3 x cubed plus x. Good. To solve for y, we need to eliminate those absolute value bars. So y minus 2 is either plus or minus 3 e to the 1/3 x cubed plus x. Which one do we go with? You really need to pay attention to the initial condition. We know from the initial condition that if x equals 0, y has to be equal to 5. Well, what happens if y is equal to 5? 5 minus 2 is 3. Specifically, positive 3. I have to have the positive version here. So I'm not going to use the negative. And now to finish this off, we're just going to say y is equal to 2 plus 3e to the 1/3 x cubed plus x. And, for those of you that want to, ask questions about domain restrictions, always a good question. I'd look at this form. I'm not dividing by 0 anywhere. I'm not trying to take the square root of a negative number anywhere. I'm not trying to evaluate the natural log of 0 or a negative number. So no domain restrictions coming in here. If you go back to the original problem, all the same things that you'd look for. Are we trying to divide by 0? Are you taking the square root of a negative number? None of those things exist. So our domain is going to be all real numbers. You could write it that way. You could say negative infinity to infinity. You could write out all real numbers. Lots of options there. Okay, let's look at the points. Here's how the College Board awards points for a problem like this. When you successfully separated the variables, 1 point. They then awarded 1 point for each of your antiderivatives. Sometimes they award a point for the constant of integration. They're not doing that here, but when you use the initial condition and find the value of c, they award the next point. And then finally, when you successfully solve the problem and say y equals blah, that's your 5th point. The domain restriction, although it's always good to think about, is not, you're not awarded a point, you don't lose a point. So in total, part A is worth 5 points. If you were able to get all the way through this, great job. This tends to be one of the places where the College Board awards the most points. This is a technique that encompasses a lot of calculus, a lot of algebra skills, a lot of functional analysis. So I hope you do well with this one. Let's move on to part B. In part B, we're told for the particular solution found in part A, find the limit as x approaches negative infinity. Well, the limit, this is part B, the limit as x approaches negative infinity, what was our function? It was 2 plus 3e to the x cubed over 3 plus x. Now, this might be a little bit tricky, but let's think about this. What happens? As x approaches negative infinity, what happens to x cubed? Well, a large negative number cubed is still a large negative number. I then have to take x cubed and divide it by 3. That's still approaching a large negative number. What about x cubed over 3 plus x? X cubed over 3 is a large negative number. We're adding it to another large negative number. So that result is still approaching negative infinity. Now here's the part we really need to pay attention. What this tells me is that my exponent for the exponential approaches negative infinity. Well, what do I know? I know that if I take e and I raise it to a power, a large negative power, what's going to happen is that that whole expression is going to approach 0. Now maybe you want to think about the graph of e to the x. Here's the graph of y equals e to the x. As your exponent approaches negative infinity, the y value is going to approach 0. That's one way you could do that. A lot of different ways. Well, let's finish it off. If we now know that e to the x cubed over 3 plus x is approaching 0, then what happens to the limit of this whole expression here? This part approaches 0. 3 times something approaching 0 is approaching 0. And then you're adding 2, so your final answer is just 2. Now, I would imagine that there are lots of you watching this video that are thinking, I could have done most of this in my head. I didn't need to do all this work. That's fine. If you can do that in your head, do it in your head. Just make sure that you clearly indicate what your final limit is. College Board just awarded 1 point for this, so we're not going to spend too much more time here. All right, let's look at part C. Okie dokie. Part C says let y equal f of x be the particular solution to the given differential equation with f of 1 equals 3. Now we want to be really careful here. This isn't the same initial condition as before. This is a different function. This is a different initial condition, which means that my function is different. Now I've seen some calculus students say, all right, let me resolve the differential equation and plug in that initial condition. Maybe, let's keep reading. It says find the value of d squared y dx squared at the point 1 comma 3. Well, what is d squared y dx squared? This is the second derivative. It's the derivative of your first derivative. So they want me to find the second derivative at this point and then decide if the graph is going to be concave up or concave down and give a reason for my answer. Well, let's see what we can do here. The second derivative means we're going to take the derivative of dy dx. Well, what was dy dx? dy dx is y minus 2 times the quantity x squared plus 1. Now I want to be really careful here so that I don't blow it with my notation. I can see that I'm multiplying the y minus 2 and the x squared plus 1. So this is already going to be a product rule when I take the derivative. I'm taking the derivative with respect to x. Well, what does that mean? When we take the derivative of y minus 2, the derivative of y with respect to x is dy dx. Not 1, we're taking the derivative of y with respect to x. That's why dy dx. So we found the derivative of the first times the second factor, plus now you leave the first factor alone, times the derivative of the second, and the derivative of x squared plus 1 with respect to x is 2x. This is d squared y dx squared. Well, we're not done because they want us to find d squared y dx squared at the point 1 comma 3. Well, what does that mean? I need to find dy dx at 1 comma 3. I'm going to multiply by x squared plus 1. Well, x is 1, so that's 1 squared plus 1, plus y minus 2, 3 minus 2, times 2 times 1. The work still to be done is in evaluating dy dx at 1 comma 3. Well, remember dy dx is y minus 2 times x squared plus 1. So dy dx at 1 comma 3 is 3 minus 2 times 1 squared plus 1. That's 1 times 2, that's 2. So I can go back over here, right? All this work was the side work to figure out the value of that first derivative. Putting everything together, dy dx at 1 comma 3 is 2, times 1 squared plus 1, that's 2, plus 3 minus 2, that's 1, times 2 times 1, that's 2. If I multiply all that out and add, we're going to get 6. Great. Feels like we're done. Find the value of d squared y dx squared at 1 comma 3. That's what this is. And then determine is the graph of f concave up or concave down at 1 comma 3. Well, how are we going to do that? Remember, we know that d squared y dx squared at 1 comma 3 is 6, and that's a positive number. Since your second derivative is positive, this means that f of x is concave up. Now be specific. Where's the graph concave up? It's concave up at 1 comma 3. That's it. That's part C. How did they award points? The College Board awarded 2 points, and they don't say how they break the points down, but they awarded 2 points for determining the value of the second derivative at 1, 3. My guess is that they awarded the first point here if you applied the product rule correctly and had dy dx. That's my guess. But what I know is if you make it all the way to 6, you get 2 points, and then 1 more point for the analysis that leads you to say that f is concave up. This is a 3-point question. And I think part C is definitely the part that's going to throw a lot of students for a loop here. But part A, pretty straightforward, should be high scoring. Part B, maybe, maybe not. But there's definitely some points in part C to be earned. Okay, hope that went well for you.